Okay, let's dive in. You've got these incredible massive AI models today, especially in vision, trained on so much data, they feel like they know everything about every image. They're powerful, right?
Oh, absolutely powerful.
But here's the challenge, making them work perfectly on a new, really specific task that they weren't originally built for.
Right.
Think about needing a model to suddenly become an expert at identifying subtle defects on a manufacturing line or, recognizing a ridiculously niche category of artwork.
And the classic approach to that, full fine-tuning, is a beast. You take the whole giant model and retrain it on your new data. It works, sure.
But it eats up computation, memory, requires huge data sets.
And frankly, it's just not practical for every scenario. It's often way too much overhead.
Totally. And that's exactly why things like visual prompt tuning, VPT, emerged. It was this really smart idea. Instead of messing with the model's core, just add a little adjustable piece, a prompt, specifically for the new task.
It's all about efficiency.
Parameter efficiency, right.
Parameter efficiency, to be precise, the key is that you're only adding or modifying a tiny fraction of the total parameters. This drastically cuts down the computational cost in memory compared to adjusting potentially billions of parameters in the full model.
Which is huge.
It's essential for actually using these powerful models in the real world where resources aren't infinite. It makes adaptation feasible,
Absolutely. It was a great step, but like all good research, people keep pushing. And that brings us to the fascinating source material. You shared notes related to an academic paper, ArcSieve preprint 2501.18936V5, provocatively titled On the Expressiveness of Visual Prompt Experts.
Right, quite a title.
Our mission in this deep dive is to unpack this paper. It identifies a key limitation in the existing way VPT works and proposes a novel, more expressive approach called Visual Adaptive Prompt Tuning VAPT. We're going to get into the academic meat of it, understanding the problem they found and the cleverness of their solution.
And what's so compelling about this work, I think, is that it doesn't just offer a new technique. It provides a deeper theoretical lens on prompts themselves.
Okay.
Which then illuminates why the existing methods hit a wall. It gives that ha moment.
Okay, let's set the stage for that deeper look then. Just to make sure we're grounded, let's briefly recap VPT again. What is it fundamentally, and why is this whole concept of parameter-efficient adaptation such a big deal right now?
Right. So imagine your pre-trained vision model is this vast library of visual understanding. VPT is like adding a new index card system to that library, specific to one topic.
Okay.
You don't rearrange the entire library. You just add these specialized index cards, these learnable prompt tokens. The model learns how to use these tokens to navigate its existing knowledge towards your new task.
So the prompt tokens are little guides, like little pointers.
Precisely. They're typically small, learnable vectors inserted into specific layers, often alongside the visual data flowing through the model.
Okay.
The model's attention mechanisms learn to interact with these tokens. Because you're only optimizing these few tokens, or a small number of related parameters, the savings in computation and memory are enormous compared to training the full model.
Right, compared to tweaking everything.
Exactly. And this isn't just a convenience. Parameter efficiency is becoming critical as models get larger and larger. Think about deploying them on edge devices, or in applications with limited bandwidth, or simply managing the massive energy cost of training. It's vital.
Got it. Efficiency is key. Now, the paper takes this existing VPT idea and looks at it from a totally new angle. This connection they draw between prompts and mixture of experts models that feels like the first big conceptual contribution, right?
Absolutely. It really is.
It changes how you think about what a prompt is doing inside the model.
Totally. This is where they introduce a more academic perspective. It's quite powerful. The paper draws on research suggesting that components within large transformer models, particularly the self-attention heads, DOT can be theoretically viewed as structures similar to mixture of experts models.
Okay, MoE models. Isn't that where you have several expert subnetworks and another network, like a gate, decides which expert is best suited to handle a specific piece of incoming data?
That's the core concept, yeah. You got it. And the paper applies this lens to prompts. They propose reinterpreting existing prompt-based methods, including VPT, not just as adding tokens, but as introducing new prompt experts into these pre-existing MoE-like structures within the model's attention heads.
Wow, okay.
It's a subtle, but I think profound shift in perspective.
Okay, so the model's attention system already acts like a committee of experts processing image information. And VPT, from this new view, is essentially adding a new specialist to that committee specifically tasked with guiding the model for the downstream task.
That's a very good way to frame it. Yes, this academic reinterpretation provides a theoretical framework to analyze the role and capabilities of prompts more deeply.
Right.
It moves beyond just it's a learnable token to it's a specialized expert contributing to the model's decision-making process. Gives it more agency conceptually.
And looking through that lens, the idea of prompts as experts, they identify a critical limitation in how prompts work in existing traditional VPT. What is that specific problem they pinpoint?
Well, based on this theoretical understanding, the paper argues that the key limitation of traditional VPT frameworks is the restricted functional expressiveness of their prompt experts.
Restricted functional expressiveness. Okay, that's dense. Let's unpack that. What does that mean in practical terms for our prompt expert committee member?
It means that the new specialist you added to the committee. In traditional VPT, that specialist is a bit rigid.
Rigid. How so?
Their advices or their contribution to the decision-making process is largely static. It doesn't significantly change or adapt back on the specific nuances of the image data that's currently processing or the fine-grained requirements of the task.
Ah.
It provides a general push, maybe, but it can't dynamically tailor its input. It's kind of like a one-size-fits-all suggestion.
See, so even if the task is identify different types of clouds, that static prompt expert might give the same kind of generic cloud guidance, regardless of whether the image is a wispy cirrus or a stormy cumulonimbus.
Exactly. It lacks the flexibility to offer nuanced, data-dependent guidance.
Got it.
This static nature means the prompt expert's ability to really specialize and contribute effectively across the diverse range of inputs it might see for a specific task is limited. This restricted expressiveness becomes a bottleneck, hindering the performance ceiling of traditional VPT,
Right.
especially on tasks that require subtle distinctions or highly variable inputs. This is the core problem VAPT is designed to overcome.
Okay, this is where the innovation really kicks in. How does the paper propose to fix this static, limited expert problem? This is visual adaptive prompt tuning VAPT. What's the core idea here?
VAPT is their novel solution, and the fundamental breakthrough is right there in the name, adaptive.
Adaptive, okay.
VAPT enhances the expressiveness of these prompt experts by making them adaptive.
So going back to our committee, VAPT creates a prompt expert who can change their advice depending on the specific data point, like reads the room a bit.
Precisely. That's a great analogy. VAPT allows the prompt experts to be dynamic. Their contribution to the model's processing is no longer static. It can change and adapt based on the input data.
Makes sense.
This means the prompt expert can offer more nuanced, tailored guidance for each specific image or situation within the task. This directly addresses the restricted expressiveness of static prompts.
And crucially,
The paper emphasizes that VAPT achieves this vastly enhanced expressiveness while still maintaining the parameter efficiency that makes prompt tuning valuable in the first place.
that's key.
They found a way to make the prompts smarter without making the whole process computationally extensive again. That's the tightrope they had to walk.
That's the real win, isn't it? Getting that adaptive intelligence without losing the efficiency benefit. Okay, so how did they prove this wasn't just a good idea on paper? What did the empirical tests show about VAPT's performance?
Right, the proof is in the pudding. The study conducted rigorous empirical evaluations on well-known benchmark datasets designed to test different aspects of vision model adaptation.
Like what?
They used VTAB-1K, which is a comprehensive collection of 19 diverse image classification tasks, things like texture recognition, natural image classification, medical image analysis, a real mix.
So it tests generalization.
Exactly. This dataset is a great test of a model's transferability to completely different domains. And they also used FGVC, which stands for fine-grained visual classification datasets.
Fine-grained, like telling apart dog breeds.
Yeah, exactly that kind of thing. Different species of birds, specific car models. These are notoriously difficult because they require distinguishing between very similar subcategories. Real detail work.
Okay, so they tested both how well it generalizes to new types of data and how well it can make super fine distinctions. What were the results compared to the standard methods?
The results were genuinely impressive, especially when compared to the computational heavyweight. Full fine-tuning.
The gold standard, sort of.
Kind of, yeah. On the diverse VTAB-1K benchmark, VAPT achieved substantial performance improvements, surpassing the fully fine-tuned baselines by a remarkable 7.34%.
Wow, 7.34% better than fine-tuning the whole model.
That's right. And on the challenging FGVC datasets, it also showed Strong gains, outperforming those baselines by 1.04%.
That's significant.
Beating full fine-tuning, which uses all the model's parameters, by over 7% on a diverse set of tasks is a really big deal. It shows the adaptive prompts are doing something really powerful.
Wow. Outperforming the brute forces method is a strong statement. And how did VAPT compare specifically to the traditional non-adaptive VPT it's trying to improve upon?
Yeah, good question. VAPT consistently outperformed traditional VPT across all tested benchmarks. No surprise there, maybe.
Right? That was the goal.
But here's another critical point for the efficiency angle. It achieved this better performance while often requiring fewer additional parameters than the traditional static VPT methods.
Wait, fewer parameters?
In many cases, yes, or comparable, but with much better results.
That is a double win. It performs better, and it's potentially more parameter efficient than the method it improves on. That's the kind of result researchers dream of, getting more for less, essentially.
It really is. And beyond these strong empirical results, the paper also provides theoretical analysis supporting VAPT's strength. This analysis indicates that VAPT achieves optimal sample efficiency.
Optimal sample efficiency, break that down for us and why it matters in the real world.
Okay. Optimal sample efficiency means that from a theoretical standpoint, VAPT is shown to be able to learn effectively and achieve high performance using the absolute minimum amount of training data possible for the problem structure.
Minimum data.
Yeah. In the real world, getting large, high-quality labeled data sets is often the most expensive and time-consuming part of deploying AI, right? Data collection, data labeling, it's a bottleneck.
So this isn't just an academic curiosity. This theoretical finding has huge practical implications.
Absolutely.
It suggests that VAPT could significantly reduce the amount of data you need to gather and label to adapt a powerful model to your specific task.
Exactly. It means you could potentially get great performance on your specific problem, like identifying those rare birds or factory defects, with far less data than you might need for traditional methods, including older VPT approaches.
Wow.
The theoretical finding kind of reinforces why VAPT works so well, suggesting it's really good at extracting the necessary information, even in data-scarce environments.
So let's pull back and look at the full picture this paper presents. We have a novel theoretical lens connecting prompts to MoE models.
Right, the Mo reinterpretation.
Which helps identify the critical bottleneck of static prompt expressiveness in current VPT. Then we have VAPT, the breakthrough technical solution that makes prompts adaptive.
The core innovation.
And finally, the validation comes from both impressive empirical results, beating full fine-tuning and traditional VPT, while being more efficient, and theoretical proof of optimal sample efficiency, meaning it's also data efficient.
That's the trifecta, really. Theory, technique, and strong validation. It's a comprehensive contribution.
It truly advances the state of prompt tuning, and this is significant for you, the listener, because it means the path to making these incredibly powerful pre-trained vision models work on your specific problems with your available resources.
It's got a lot more accessible and effective. Whether you have limited compute, limited memory, or critically limited data, VAPT points towards a future where you can still leverage state-of-the-art vision models effectively.
It lowers the barrier to entry for specializing these generalist powerhouses. It's worth noting, as we saw in the source material, that this research comes from a team including Minh, Nguyen, Nguyen, Chau, Tran, and Nhat.
Right, acknowledging the authors.
And the journey from V1 on ArcSieve in January 2025 to the current V5 in June 2025 highlights the iterative nature of pushing these academic boundaries, refining ideas, and strengthening results over time. You see the work evolving.
That evolution on ArcSieve is a story in itself, isn't it? Showing the process of scientific discovery and refinement in near real time.
Absolutely. So to recap this deep dive, we started with the challenge of adapting massive vision models efficiently. We looked at VPT as an initial solution.
A good starting point.
This paper offered a deeper academic understanding by framing prompts as experts within MoE structures, which revealed the crucial limitation of static prompt expressiveness.
The theoretical insight.
And then the innovation, visual adaptive prompt tuning, VAPT, which overcomes this by making prompts adaptive.
The practical solution, VAPT.
This was validated by strong empirical results on VTAB-1K and FGVC, showing VAPT outperforms both full fine-tuning and traditional VPT, while also being more parameter efficient.
And theoretically achieving optimal sample efficiency. Don't forget the data efficiency part.
Right. So you've now taken a deep dive into research that's making powerful AI adaptation both more effective and more efficient, tackling the real-world constraints of compute, memory, and data scarcity through a clever technical and theoretical advancement.
So here's a final thought to leave you with. Considering VAPT's success in making prompt experts adaptive, what other fundamental, seemingly static components or mechanisms within large AI models could potentially benefit from a similar injection of adaptive expressiveness?
Interesting.
Where else could making parts of the model more dynamic and data-aware unlock even greater potential, especially when you're working with limited resources? That's a thought to carry forward.